So what we're going to see, and in addition to the two different options that we've already discussed, which is that they are different or homotopic protons, we actually have two other options for these hydrogen atoms as well, and they're a little bit less obvious than the identical or different. So this third case here is what we call enantiotopic proton. So this, what do I mean by that? Well, if we go over here into this ChemDraw file and you look at this compound here, so this butane molecule, the green proton and the blue proton, and I replace each one sequentially with an X. So I replace the blue one with blue X or the green one with green X, and now I ask myself, what are these two molecules? Well, it turns out that they are not exactly identical. They are actually enantiomers of each other. So these two H's are called a pro-S hydrogen or a pro-R hydrogen. That means if you replace this H, then that gives me an S-configured chiral center, and if you replace this pro-RH, that gives me an R-configured chiral center. So the two hydrogen atoms that I'm talking about now, this pro-R and this pro-S one, these are called enantiotopic hydrogen atoms. So that's my third option for what these, whether my hydrogen atoms are chemically equivalent. My fourth case, and this is an interesting case, where I look at these only in the case where I have a chiral center already in the molecule. Now if I replace these two H's, this green H or this blue H, do the same swapping end of an X for each atom separately, these two molecules that result here are actually diastereomers of each other. So just to review, diastereomers are stereoisomers that are not enantiomers. So the chirality at this center here is the same as what I've shown here, meaning I have enantiomers at this particular chiral center, but because I have a chiral center elsewhere in the molecule, so that's this guy shown over here, that makes these two atoms these two molecules diastereomers, stereoisomers that are not enantiomers. And in this particular case, these H's, the green H and the blue H, are therefore now called diastereotopic. And that's what I show here, diastereotopic, and that's only seen in cases where there is a chiral center already existing in my molecule. So what I'm going to do now, just to try to help understand these concepts a little bit better, is to actually go through some examples of molecules and identify whether protons in question are chemically equivalent homotopic, completely different, chemically non-equivalent, or enantiotopic, or diastereotopic. So which of my four cases, so shown here, are they different, homotopic, enantiotopic, or diastereotopic? So let's look now at this case over here, and focusing in particularly on these two red protons. So what I'm going to do here is what I've shown you how to do, is to replace each one sequentially with an X. So here's the one where I put the X pointing away from me, and here's the other choice where I point the X coming out of the board to me. These two products here that would result if I swap out each one for an X, these two products are enantiomers of each other. These are enantiomers. The protons are enantiotopic. Enantiotopic protons give you only one signal in the NMR. So both homotopic and enantiotopic protons give a single NMR signal. Diastereotopic ones, in contrast, actually give us different signals. Alright, so let's now look at this case over here, this molecule. Now if I swap out each hydrogen for an X, and I look at the products that result, these are actually diastereomers of each other, because in addition to having now a chiral center here, what I have is a chiral center here at this OH substituted one as well. Second chiral center in the molecule. That gives me stereoisomers that are not enantiomers. That means that the protons in question are diastereotopic. And again, diastereotopic protons give unique signals in the NMR. let's look now at this example over here. So this alkene, now again I'm going to replace the top one with an X and also the bottom one with an X and ask what's the relationship between these two products. Here, the one where the X is in this position versus that position. So here in this first alkene product, you can see the methyl groups are on the same side. Here you can see the methyl groups are on opposite sides. This is yet another case where I have stereoisomers that are not enantiomers. Therefore, these are diastereomers, and the protons are diastereotopic, gives unique signals by NMR. And finally, I'm going to do one more example over here, and that's if I take this molecule and replace these two protons each with an X sequentially, this is again another case of diastereomers and diastereotopic protons. Diastereomers, diastereotopic protons. That means if I look at the CH2, I would initially say the CH2 protons are chemically equivalent, but in fact, because of this chiral center elsewhere in the molecule, what I'm going to see are two different signals, one for each of these diastereotopic protons. So now let's go through what useful information you can get from a proton NMR spectrum, and that's related substantially to the chemical shifts that we see in the protons, which correlates with their local chemical environment. So the same way that we see distinct chemical shifts for carbon-13 NMR, we also see distinct shifts by proton NMR, and again that correlates with how much the neighboring atoms are or are not able to shield those protons from the applied external magnetic field. And you can find a table in your book that talks in detail about where you're going to should see different protons in the NMR spectrum. And here I'm just going to show you, so this is not exactly the same one from your book, but it gives you a gist. So the x-axis here is my scale in ppms, and again that's reference to TMS or tetramethylsilane, which is set to 0 ppm. And what I can see here are all different kinds of protons. So let's start with the one down here. So this is the deshielded area. So again, these are things that are not protons that are not being shielded well by other parts of the molecule. And you can see way down here, carboxylic acid protons are the least shielded. And then you see aldehydes, other aldehydes are also way down here, as well as, I guess the old ketones don't have things directly attached to them. Okay, so these carboxylic acids and aldehydes, these are the least shielded. The saturated alkanes are the most shielded. Other unsaturated protons, so protons attached to unsaturated carbon atoms, show up less shielded, and certainly ones that are attached to heteroatoms like an OH group or an ether, as are showing up in this region as well. So they're less shielded than saturated alkenes, but they're still more shielded than the sp2 carbonyls. What's interesting is that the aromatic region, I want to draw your attention to this area, aromatic protons are very deshielded, and they always show up in the 6 to 8 ppm range. So that's very characteristic. Very characteristically between 6 ppm and 8 ppm. And that's clear. If you see a spectrum that has peaks in that region, you can say right away that that definitely has an aromatic ring in it. And conversely, if you see an NMR spectrum without peaks in the aromatic region, it is automatically clear that there is no benzene ring position anywhere in that molecule. And we can pull up a number of different tables for where these proton shifts appear. So let's just look at this one also, for example, where you can see the arenes. Let's see if we can see this better. I don't think we can see this well. So you can see the different regions, and again that corresponds to how shielded or unshielded each of these protons are by the rest of that molecule. We're going to do a few examples now, trying to predict where NMR signals for protons would appear in the molecule. So, starting on this side of this ChemDraw file here, this cyclohexane has only one proton signal, because all the protons in the molecule are chemically equivalent. And because this cyclohexane here is a saturated alkane with no heteroatoms, if I go to my table and I see saturated alkanes, those are usually between 0 and 2 ppms. So where would these protons expect to show up? Expect a proton NMR signal between 0 ppms and 2 ppms for the cyclohexane. Now, if I go to look at this next example over here, this acetone, again, I have only one type of proton in the molecule, so I am going to see only one signal in the NMR spectrum. Where is that going to appear? Well, I go to my table and I see where are my ketones showing up. So that would be this kind of system here. The H is attached to a carbon that is bound to a ketone. Showing up are between 1 and 2 ppms. And acetone, in fact, shows up right at 2 ppms. I'm going to put that into my ChemDraw here too. Saturated ketone at 2 ppms. That goes to this guy. Benzene, again, this is an aromatic ring. All the protons here are chemically equivalent as well. And so I'm going to see only a single signal. I go to my table, I remember characteristic proton signals for an aromatic region are going to be between 6 ppms and 8 ppm. Methylene chloride, again, chemically equivalent protons. Where do they show up? Well, I look at my table here. Where do the chlorides show up? That's between 3 and 4 ppm. So I hope this is helpful for you in trying to figure out where the different atoms show up, or how the local environment of the molecule really affects the chemical shifts of the proton. Now look at this molecule here. These are pretty much among the least shielded protons you can imagine, because the carbonyl group is pulling, the oxygens are pulling electron density towards themselves in general, and these are sp2 hybridized carbons that they're attached to. So these protons are going to show up way downfield, very deshielded, near 10 ppm. And then finally, in this last example, this is trimethylamine shown over here. Where does this show up? Well, if I look at my signals, I can see that that shows up around 2 ppm for a saturated amine. So now we're going to talk about more information. So in addition to the chemical shifts, which correspond to the environment, what other information can I get from a proton NMR spectrum? And that really comes to the question of integrating peaks, so looking at the area under the curve. So just to be clear, when we're talking about the carbon-13 NMR spectrum, you will see carbon NMR spectrum will show you peaks with different heights. That does not correspond to the number of carbons. So those peaks have different heights and different intensities. That's not related to how many different carbons are contributing to each signal. So you cannot, absolutely cannot integrate those areas and figure out how many chemically equivalent carbon atoms are involved in each peak. However, for the proton NMR spectrum, you absolutely can. So here, the area under the peak for each NMR peak in the proton spectrum corresponds to the number of chemically equivalent hydrogen atoms that generate that particular signal. And I can see that, let's see if we look at this example here, let's look at methyl, hold on, where is this peak? Methyl propanoate, this guy, methyl 2,2-dimethyl propanoate. I'm going to draw that structure in ChemDraw here. So those three guys, and then here, this carbon here is going to have a carbonyl on it. Hold on, let's draw what these guys actually look like. And the question now is, the first question is, if I look at a molecule like this, how many different proton signals am I going to see? Well, I'm actually going to see only 2 proton signals because these 3, hold on, these 3 are chemically equivalent, these blue guys, and these 9, so this T-butyl, these 9 are actually all chemically equivalent as well. So what I'm going to see are 2 signals in the proton NMR spectrum. And in fact, the area under the curve, under the peaks for each of them are going to be proportional to the number of protons. So one signal can be integrated to 9, and that's going to correspond to the red. Integrated to 9 protons. And one signal will be 1/3 of that size and correspond to 3 protons. And that's going to be the one that corresponds to the methyl group directly attached to the O over here, this methyl group. So again, if I look at what that spectrum actually looks like, let's see if we can pull that up. Nope, hold on. This guy here should show me that. Here, let's zoom in on this peak over here. I can see a peak here at 3.6 ppm, and that is 1/3 the size of the peak at 1.2 ppm. That's how I know that this peak corresponds to 3 protons, and this peak way down here corresponds to 9 protons. Also, it's important to note the chemical shifts here are what you would expect. So the CH3 that's directly bound to the oxygen, the protons from that signal are less shielded, and so therefore at a higher ppm value than the protons that are involved in this T-butyl group. Those are more shielded. Those show up again at a lower ppm value compared to the other protons in the molecule, and the integrating, the area, or the integration of this peak down here is 9 protons compared to this peak over here, where the integration of this one is corresponding to 3 protons. So what you can see also, and you can see this if you start looking at NMR spectra, proton NMR spectrum, is that oftentimes you see single peaks like this, but a lot of times as well you end up seeing these weird, what we call splitting patterns here. And for example, if I look at this bromoethane peak of spectrum corresponding to this bromoethane molecule, what I actually see is that the signal corresponding to the purple shows up at 4 little peaks, and the signal corresponding to the blue shows up at 3 peaks. So I see a cluster of peaks now at a 1.68 ppm and a cluster of peaks at 3.42 ppm, and this one can be integrated, the blue peaks are integrated to 3 and the pink peaks are integrated to 2, and so I get now again I get the information, the chemical shift, that's one piece of information, integration is a second piece of information, and now the splitting is going to give me even more information. So let's review this. So far from NMR spectroscopy, we've been able to see that chemical shift shows me the local environment, and then integrating the areas under the peaks shows me how many protons correspond to each signal. Now I'm going to take this one step further and figure out what information can I get from splitting. What information can this splitting pattern give me? So let's go back to this bromoethane example over here. So this is called, so why do we see this splitting? Well, it turns out that the local environment felt by each proton is actually affected even more subtly by the neighboring protons. So if I look at this bromoethane, so let's draw that again over here. Hold on, let's give it some more space. Looking at this bromoethane, and focusing in particular on these CH2s at the middle. Hold on, we'll put those guys in too. So look at these. Let's look at these CH3s at the end here. Each of these H's can be either aligned or parallel or anti-parallel to the magnetic field. So what I'm going to see now, if I look at each of these H's, I'm going to see now parallel, parallel, parallel. That's one possible configuration for these protons. Parallel, anti-parallel. That's a second configuration, okay? I can also see parallel, anti-anti. And I can see anti-anti-anti. So those are, so if I have 3 protons, I have 4 possible configurations. Three protons gives me 4 possible configurations in terms of the orientations of the protons, and that's always going to be true that n protons gives me n plus 1 configurations. N protons gives me n plus 1 configurations of possible spin alignments or misalignments. Now, and again, now I'm talking about the possible arrangements of these protons in particular. And we'll make all of that red to be clear. Now if I look at these protons over here, it turns out that their local environment is going to be slightly different if they're next to a parallel, parallel, parallel than it would be if they're next to an anti, anti, anti. So the local environment on the neighboring atom is slightly different depending on the spin orientation of the protons on the neighboring carbon. Meaning, if this proton here is next to a parallel, 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 it will give me one signal. If it's next to a parallel, anti-parallel, it will give me a separate signal, slightly different. If it's next to a parallel, anti-anti, it'll give me yet a third signal. And if it's next to an anti, 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 then it's actually going to give me a fourth distinct signal. And what that gives rise to now is a cluster of 4 peaks. Okay, I have 4 different peaks. Instead of seeing 1 peak for these protons, what I'm going to actually see is 4 peaks for these protons, and they're all going to be clustered together, and where each of those peaks in the cluster, each peak in the cluster corresponds to a different arrangement of spins in the adjacent carbon, in the protons on the adjacent carbon. And now if I go back to what that spectrum looks like for bromoethane, I can see, so this is the CH2, it's being split into 4 different peaks because on the neighboring carbon it has 3 protons, and each of those, and those 3 protons can be aligned in 4 different ways. What I'm also going to notice here is that the heights or the intensities of each of these peaks in this quartet is different. That's because this peak here, let's say, is all parallel, if the three H's are all parallel. This peak here is if all the three H's are anti-parallel, but there's more of a likelihood of having these two in between states. All right, so these are not all equally likely. I'm going to have, let's say, one part parallel, 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 two like that. No, sorry, three like that, 3 to 1. So it's going to be split to non-equal peaks where I only have one possibility of parallel, 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 but if I want to have one anti, I could have parallel, anti-parallel, anti-parallel, parallel, 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 anti. So 3 different states can give rise to this middle peak, and again 3 different states can give rise to this peak, but only one state to that, so that's why those peak heights are not the same. I'm going to write that out, so because that's a little bit confusing as well for people, but that's why the peak that corresponds to this proton is going to show up as a quartet. So let's see. Again, the one peak of the quartet is for parallel, parallel, parallel. I'll just abbreviate that P. Second peak of the quartet corresponds to PAP or APP or PPA. Third peak of the quartet corresponds to PAA or APA or AAP. And then the fourth peak corresponds to AAA. So again, I'm going to see 4 peaks. These two, the two on the ends, are going to be one height. The 2 middle ones are going to be 3 times that height because they have 3 different states that are all identical energetically. And in general, broadly, 3 protons on this carbon, or n protons on this carbon, gives rise to n+1 splitting patterns. I can now go through, so I see that, hold on. Over here, you can see this kind of splitting pattern for the pink protons. This is a quartet, and the reason it's a quartet is because it's coupled with the adjacent CH3. Now if I look at the other protons, so if I now look at these red ones and I say, what are they split into? Well, that's going to depend on the CH2s. So here, I now have 3 protons, 2 protons in the CH2. They're going to be split by, sorry, 1 second, hold on. Okay, so the CH2 is a quartet, but now I'm going to ask myself, what are these CH3s going to look like? Well, the CH3s are going to be split by the CH2. So my CH2s can be parallel, or both anti-parallel, or one parallel and one anti-parallel, which means that these protons here are going to be split into a triplet by virtue of being coupled with a CH2 group. And that triplet is again going to have 3 different states. So first peak of the triplet is going to be PP, second peak is going to be AP or PA, and third peak is going to be AA. So again, those peak heights are not going to be identical either. You're going to see a 1 to 2 to 1 splitting pattern from that triplet, and that's what I see here, a 1, this case, to 2 to 1, that's the triplet. And then I also see here, again, this quartet is 1 case, and then I hear 1, 2, 3. The intermediate ones have 3 different cases depending on the alignments of the spins. And then this fourth case here, again, is only 1. That's a quartet due to coupling with the CH3. This guy is a triplet due to coupling with the CH2. So again, this is the CH3 peak, but it's split because it's coupled to a CH2. This is the CH2 peak, but its splitting is determined by the coupling with the CH3. And I can calculate the difference, or this coupling constant J, between which is the distance between the peaks within a multiplet within the splitting pattern, and those are going to be identical. So if these are splitting each other, then they're going to have the same coupling constant. So this distance is going to be 7 Hertz. This distance is going to be 7 Hertz as well. So in general, we can have an n+1 rule, which is that protons that have n equivalent neighboring protons show n+1 peaks in their NMR spectrum. So here we're looking at this molecule. I'm going to draw that one separately as well. Here, let's look at this molecule. This molecule is this 2-bromopropane. 2-bromopropane. So the first question is, how many hydrogen atoms do we see? We have 7. How many different hydrogen atoms do we see? Well, we only have 2 chemically distinct hydrogen atoms, distinct groups. And because these two CH3s are identical to each other, this signal for the CH3s will integrate to 6, and the signal for the CH will integrate to 1. So that's the first information I can get. 2 distinct groups. I can get the integration values for both of them, and then the third thing I'm looking at is the splitting pattern. So here I can see that the signal that corresponds to the CH3s is going to be split into 2. That's because they're next to a carbon that has 1 proton on it. Okay, so this is N, therefore they're split into N+1. So they have 1 proton. The signal for these is split into a doublet. That's these 2 over here. And this proton here has on the how many protons are on the neighboring carbons? 6. So because there are 6 protons on the neighboring carbons, this proton in this middle is going to be split into what's called a septet, split into 7 signals. Middle H is going to be split into 7 unique signals, called a septet, by virtue of the fact that on the neighboring carbon atoms you have 6 different protons. And here what I'm going to show you is what the ratios of the intensities are. So we've looked at the doublet and the triplet and the quartet. This again depends on that spin alignments of the neighboring protons, but you can see that up to, so you have a quintet or a septet, you can see how the intensities of the signals is going to depend on the different arrangements of the spins on the neighboring carbons. So again, a singlet only has 1 peak. Okay, a doublet, the 2 peaks are of equal size. A triplet is a 1 to 2 to 1 intensity ratio. Quartet, this is we saw with the bromoethane, 1 to 3 to 3 to 1. You have a quintet and also a septet now with more complicated intensity ratios. But again, this is pretty useful information in terms of what we can get from the molecule. So let's go through some rules about chemical split, about spin-spin splitting in proton NMR. So the first rule is that chemically equivalent protons do not split each other. So if I look at this molecule here, this is C. Hold on, let's see if we can make this bigger. These are chemically equivalent, they don't split each other. These 4 are chemically equivalent, they do not split each other. That's because the chemically equivalent protons are not changing the environment of other protons that are the same sort of local chemical environment. The other thing, right, is that the signal of a proton, this is what we talked about, with n equivalent protons is split into a multiplet of n+1 peaks, okay? So if this carbon here, I look and I figure out how many protons are on the neighboring carbons here. If there's only 1 neighboring carbon, we're going to see this split into 2 peaks, so n+1. The final thing is that what we don't do is we don't look at sort of long-range splitting. So things are only split, proton signals are only split by the immediate local environment. Okay, so this proton over here is not affected by the spin states or the possible spin states of this proton. So the splitting again is only determined by the protons on carbons that are directly attached to it. And then an additional rule, again, is that 2 groups of protons that are coupled to each other have the same coupling constant. So if I look at this molecule over here, this paramethoxypropiophenone, okay, don't worry about the nomenclature for now. This CH2 is split by this CH3, and this CH3 is split by this CH2, Okay, so their distances in the splitting patterns are going to be identical. Their coupling constant J is going to be the same. They're separated by the same hertz. This CH3 here, if I ask how many singles is that going to be split into, well, there are no protons on immediately adjacent carbon atoms. There are no immediately adjacent carbon atoms, period. So that's going to be a singlet. And that's what I see as this green peak over here. Now with the aromatic ring, I can see there's an H, 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 H. So these two H's, this H and that H, are chemically equivalent. And then these two are also chemically equivalent. These are going to be split into a doublet, and these are going to be split into a doublet. I'm going to draw out what this para-substituted compound actually looks like, so we can review that information in a little bit more detail right now. Hold on, let's find that. So again, we're going to draw this para-substituted ring here and try to explain the splitting pattern, particularly in the aromatic ring area. So, focusing first on the non-aromatic ring protons, hopefully by now it's a little bit more straightforward. We're going to color them also different colors. We're going to make these guys red. No, we're going to make them green. Make these guys green. So this is a singlet because there are no protons on neighboring carbon atoms. That singlet is relatively de-shielded because it's pretty close to the electronegative oxygen atom. And the area under this peak is going to correspond to 3 because there are 3 chemically equivalent protons that gave rise to that signal. So overall, that's what I see over here at 3.84 ppm. Now, let's focus on these protons here. This is a CH2, and this is split into 4 because it's directly attached to the CH3 group here. So it's going to be split into a quartet. The area under this curve is going to correspond to 2 because there are 2 chemically equivalent protons that gave rise to that signal, and they're going to be moderately, I don't know why it's yellow, moderately de-shielded, again because they're pretty close to this O here, and that overall is going to give me this blue quartet that I see here. This CH3 here is going to be split into a triplet, so 3 separate peaks because of its proximity to the CH2. The area under that curve is going to equal 3, corresponding to the 3 protons, and it's going to be fairly shielded because this one is more removed from the electronegative atoms in this particular molecule. So that's as far as the splittings and the peak positions of the aliphatic groups. If I now start and look into this aromatic ring, this para-substituted aromatic ring, what I'm going to see is that I have 2 sets of chemically equivalent protons. And that's always going to be true for para-substituted rings. That what I have, we're going to make these guys red, and we're going to make these guys, I guess, purple. So the red protons, so I have 2 sets of chemically equivalent protons in an aromatic ring. And that's always true for para-substituted benzene rings. If you want to test that, you can substitute each one with an X sequentially and then see whether that gives you the same or different molecules, or you could just take my word for it. Para-substituted rings give us 2 sets of chemically equivalent protons. So the chemically equivalent ones do not split each other, but this set, the red guys, are going to be split into a doublet because it's close to the purple. And the purple is going to be split into a doublet because of its proximity to the H's on their neighboring protons, so the red protons. So these split each other now into a doublet. So para-substituted rings always give 2 doublets in the aromatic region. we're going to practice this, and I hope you practice this quite a bit on the problem sets, but it should become very easy to see if the molecule in question is a para-substituted aromatic ring, because you will always see two doublets. Two doublets in the aromatic region always means para-substitution. And that's what we see here in this particular case for this molecule. You see one doublet around 7.93 ppm and one doublet around 6.9 ppm. I can also ask which one is going to correspond, the red or the purple will correspond to the 7.9, which one is more or less shielded, and I can figure out that the red protons are more shielded, therefore they show up at 6.9 ppm. The purple protons are less shielded, again because that carbonyl is more electron withdrawing than the methoxy group, and they're going to show up at 7.9 ppm. So you're actually getting a tremendous amount of useful information from this NMR spectrum, especially when we start adding in the peak position, the peak integration, the area, and now the splitting patterns as well. It really starts to give us a tremendous amount of information about the system. So you may be wondering to yourself why there's no splitting in carbon spectrum, and that's a good question. So if you are wondering that, that's fabulous. The reason there's no splitting in a carbon spectrum is because you have a very low natural abundance of carbon-13 that makes it pretty unlikely that two carbon nuclei are going to be close to each other in the molecule. Okay, and the reason you don't have splitting, so the protons you have no carbon-hydrogen spin coupling, because of what's called broadband decoupling. Okay, so that means that when you're actually running this carbon-13 spectrum, you irradiate the molecule with a pulse of RF frequency, and that what you have in this particular case is that the hydrogens spin flip pretty rapidly so that their local fields average to 0, and the carbon atoms are not seeing any different environment depending on the fields. But that's a good question. Now let's do an example together, and that's what they show here. Let's say I have a molecule C5H12O that has the following NMR data. It has a triplet. Here, I'm going to put this here so we can do it separately here. Add a triplet that corresponds to 3 protons, a singlet that corresponds to 6, a quartet that corresponds to 2, and a broad singlet that corresponds to 1. Okay, so let's do the first thing, C5H12O. The first thing to note is that broad singlet almost always means alcohol. Broad singlet means an OH group. That's because OH groups tend to be broad because you have a lot of hydrogen bonding, which means that the H's that you see from an OH group are actually, that signal is actually an average of a number of different OH groups, each of which has a slightly different local environment because of the different degrees of hydrogen bonding. The second thing we're going to see if we look at the ppms are you have no aromatic rings at all. They're all in the saturated region, so I'm going to have a fully saturated alcohol system. I can confirm that saturation by looking at the degrees of unsaturation, so CnH2n plus 2, C5H12, so that's good. It's certainly fully saturated. I can now start to look at the splitting and try to figure out what's going on. So I have 4 different types of protons, even though I have 12 protons in the molecule. The fact that I have 6 H's that are a singlet means that I have 2 chemically equivalent methyl groups. So let's draw that. I have 2 chemically equivalent methyl groups, but they're a singlet, so that means that there can't be any H's on this molecule, or else they would be split. So let's say if I make one of these, put my OH right there, and put another carbon there. Let's see if this gives us something useful. Okay, so now I have, let's see, a triplet that corresponds to 3 H's. So that's this. A terminal methyl group always gives a triplet for 3 H's. Or if it's attached to a CH2, right? So not exactly, not always. If I have an ethyl group, so if I have a CH2, CH3, that's going to give me a quartet for 2H and a triplet for 3H. Okay, so this CH2 is going to be a quartet corresponding to 2 H's, and the terminal methyl, that CH3, that's directly attached to the CH2, is going to give me a triplet. So if I look here, I have a triplet for 3 H's, that's this guy. Let's make him red. I have a singlet for 6 H's, that would be these two because they're not attached, their neighboring carbon has no protons on it. Okay, I have a quartet for 2 H's, so that's going to be this ethyl over here. Let's make these things purple. Purple is always a nice color for us. Purple. And then that broad H that corresponds to the alcohol is what I see over there. And also noteworthy, these coupling constants, so the purple couples with the red couples with the purple, and therefore their coupling constants are equal to each other. So they're both going to be 7 Hertz in this particular case. So let's see if they work through the example in the same way. Look at each absorption individually. So this is the strategy here. The 3-proton environment is a methyl group. Okay. So you can go through this logic here as well, and you get a structure that looks like this. So we were right. Good job, guys. Nice job. So I'm going to upload this particular PDF as well, but what we can do, hold on, let's see. There are a number of potentially more complicated splitting patterns. So this is that different hydrogens, for example, may have overlapping signals, okay, even if they're not chemically equivalent. So if I look at toluene, and this is the case that we're seeing over here, you have the CHs corresponding to this methyl group. That's a singlet, that's fine. But the toluene signals have, so just the single monosubstitute, the benzene ring actually has 3 chemically non-equivalent, three groups of protons, right? Chemically equivalent protons, the ones that are ortho or meta or para to that substituent. So in theory, you should see 3 different signals. What you have with the case of the toluene is accidentally overlapping signals. You actually see only 3 signals for that. So let me show you what I mean for this toluene molecule. So this is toluene. In the aromatic region, you should have 3 groups of protons. So the orthos are chemically equivalent to each other. The metas are chemically equivalent to each other. And the para one is not chemically equivalent to anything else. And what you should be seeing is splittings where the ortho guys, those are my orthos, my metas and my paras. So in theory, these orthos should be split by the metas. The metas should be split by the para and the 2 orthos, and the para should be split just by the metas. But because these signals end up being so close together in energy, you just see a situation that looks like this. This is a monosubstituted benzene ring. What you can also see, and this is where things get a little bit more complicated, is that a single signal can be split by 2 or more non-equivalent protons. So what do I mean by that? Let's look at this example of trans-cinnamaldehyde. That's this guy here. Let's draw this structure and try to figure out together what it should look like. So if I look at this structure, what I can see, let's focus first. Okay, let's start with the easy one. This is my aldehyde guy. We'll make him pink. Alright, he's not split by anything. There are no protons on neighboring carbons. Okay, he's way down here. He's very de-shielded. He integrates to 1. Everybody's happy. Now, let's focus now on the aromatic region. So here we have an ortho-substituted, or mono-substituted benzene ring, which is going to give me a mess in the aromatic region. Those are the black protons that we see here in the spectra. Here, so let's put those all in. Now, what becomes more interesting is looking at this proton here shown in green, and this proton guy over here shown in blue. So this green proton is on this carbon. It has on its neighboring carbons only one H. Okay, so this is going to be split into a doublet by virtue of this H. Alright, so that's good. That's what I would expect to see. Right, because it only has one proton on the neighboring carbon. This carbon has no protons on it. Green H is a doublet. Now, blue H, on the other hand, has on the neighboring carbons, this neighboring carbon has one H. This neighboring carbon also has an H. It has an H that's in a very different environment than this green H here. So it's going to be split, and this splitting is actually totally not predictable as far as we know. It's not split by the n+1 rule at all. So in cases where it's split, where a single signal is split by non-equivalent protons, that's not predicted by the n+1 rule at all in that particular case. So here you end up seeing what's effectively two doublets for the trans-cinnamaldehyde, but that's pretty difficult for predicting values. So this just writes out some of that logic together. So the H-NMR spectrum of trans-cinnamaldehyde, you have 5 aromatic protons, okay, and the aldehyde signal is normal. The vinylic proton signal at C3, okay, is next to the aromatic ring. So actually the aldehyde signal is split. Let's look closer at that. Hold on, let's make sure we can see that together. This aldehyde actually is split into a doublet, okay, and this green one is shifted because it's close to the benzene ring. It's conjugated to the aromatic ring. It's a doublet. That makes sense to us. The C2, this blue guy, is actually more complicated, and its splitting can be classified as a doublet of doublets, okay? So green splits it into a doublet, and pink splits it into a doublet, and it actually splits into 2 separate doublets. So if you calculated, these coupling patterns are actually different from each other, these coupling constants, sorry, because they're being split by chemically non-equivalent protons. And then finally, let's just do one example together of where you might see NMR spectroscopy actually being used. So if I take this methylene cyclohexane and I react it through hydroboration oxidation to form an alcohol from that alkene, and I want to ask myself which carbon, what was the regioselectivity of this oxidation reaction? Did the OH end up on this CH2, or did it end up on this C over here in the middle? And I can use NMR to figure that out pretty easily by, let's see, my product here is this one with the CH2OH. If I did form this CH3, this alternate product, what I would see is a singlet for a methyl group, which I don't see at all. Alright, so that's this singlet for the methyl group. This CH2OH is going to show some pretty straightforward splitting patterns, and in particular, this CH2, which is my new group of the molecule that I'm forming, is going to be split into a doublet by the proximity of this H. Okay, so let's draw that as well. What I do form in this case is CH2OH, and this is my new signal. Hold on, let's draw that. And I can look at the new CH2 group that I form and see that it's actually being split into a doublet. So this is my new CH2. That's going to be split by the proximity of this H. The alternate product that I don't form would look like this. Hold on. And this CH3 would not be split at all because there are no protons on adjacent carbons. Sorry, I can't actually get that OH. Hold on, let's try it now. Good. There are no protons on adjacent carbons, so that CH3 will not be split at all. So the new signal, in this case, the fact that I see a new signal, that new signal is split into this doublet, shows us that we form the OH at that position, so the regioselectivity. Now it's actually, okay, so it's a little bit more complicated than that, because in addition to this CH2 being split by this H, it's also split by the H on this oxygen. Okay, so this oxygen OH splits it, this splits it as well. You end up getting a multiplet instead of a distinct doublet or any distinct splitting pattern. You end up getting what we call a multiplet, which is basically a fancy way for saying we can't really characterize that splitting pattern selectively. But it's pretty clear that in all cases, what you're not seeing is a new singlet being formed in this particular case. So that's it as far as NMR spectroscopy goes. We're going to go on Friday. So the Friday quiz does cover all of this information with an emphasis on what we did in class. I would encourage you strongly to look at the problem sets and use those as practice for the quiz. We're going to go through on Friday how to start putting all of this information together and get structure determination, really do a full sort of puzzle solving session there.